Oh dear. There we go. Yes, yes. Good morning. Oh dear, this is all slanted. There we go. Alrighty, so let's just start off this morning just doing a little bit of review just to see if we remember what we did yesterday. So I would like you to classify the following substances as either pure substances or mixtures. And if they're a pure substance, go ahead and classify them as either an element or a compound. And then if it's a mixture, if it's homogeneous or heterogeneous. Okay, so how about we do... Let's do iced coffee as one of them. Let's do lead. And how about we do... Let's see. How about wine? And one more. How about we do chalk? Oops. Which is that, by the way. So go ahead and just kind of write in the chat box there what you think these four things are. In terms of like how we would classify them as matter. And I know you guys are kind of trickling in since we just started the stream. Very good. I like that answer. Absolutely. Definitely a homogeneous mixture. There's definitely a lot of different things going on in there. You have, of course, water. You have ethanol. You have all the different, flavoring and color compounds in there also. And it should all be the same throughout. So, like, no matter where you look in the wine molecularly, it should be the same. Yep, I like your answer there also. The iced coffee should be heterogeneous, right? Because of having that ice, right? So, because if you take a thing of iced coffee, you'll see, chunks of ice at the top, right? And then there will not be ice on the bottom. So as a result, because you have different, composition in there, it's going to be a heterogeneous mixture. Alrighty, let's see here. So, alrighty, okay, so I agree that lead is going to be... Here, I'll just put this down here. That is a pure substance. And it's an element. We'll see that on the periodic table. Um, so Paulette, technically, we want to only use homogeneous or heterogeneous for mixtures. Some of these are not mixtures, so we want to avoid using those words if it's not a mixture. So, for example, the lead was just a pure substance. So even though it is homogeneous, yes, it's the same thing. We just don't want to use that word because it's not a mixture. Okay, and the chalk. So I see elemental compound in there. It's not both, right? It's either an element or a compound. So which one do we think that's going to be? Yeah, yeah. So that's going to... and how do we know it's a compound? Oh dear, my tablet is like melting today. Um, yeah, exactly. You have different elements in there. You have calcium, you have carbon, you have oxygen. Multiple elements in the same thing is going to be a compound. So give me a minute. I'm just going to go ahead and restart the tablet. Let's see if that is going to fix this. In the meantime, does anybody have any questions for what we did yesterday? So yeah, so we also talked about energy, right? Just kind of vague, briefly talking about kinetic versus potential energy. And we talked about the scientific method a little bit. So any questions on that stuff? Alrighty, cool. So today we're going to continue talking about matter, as we will for probably the whole day. We'll be still talking about matter. So a substance cannot change, but a mixture could. Yeah, totally. So yeah, if your milk goes chunky, you'll absolutely have a heterogeneous mixture. Yeah, definitely. And then the same thing, if your iced coffee, if all the ice melts, and you mix it up, then it's going to be homogeneous now, right? So it just kind of depends, as you're looking at things. So, okay. Tablet has restarted. Let's go ahead and reconnect it here, and hopefully that'll make it nice and smooth. But typically we're only looking at these things as a kind of like one instance in time. So we're not worrying about the iced coffee melting or the milk going bad. Alrighty. So, in this case, let's go ahead and continue here. We're going to now talk about states of matter. And I'm sure you have heard of these before, right? You have solids, you have liquids, and of course, gases. You do have other states that we're not going to talk about in this course. You have plasma, you have supercritical fluids. We're not going to worry about those. So we're just going to talk about solids, liquids, and gases in this class. So, I'm going to ask you, how do we know if something is solid? Or liquid or gas? How do you know these things? Anyone at all? Yeah, I like it. So we have solids hold their shape, right? So that's a big part. And they have their defined volume as well. Yeah, absolutely. So, let's see. Stapler here, our heterogeneous mixture, right? Our stapler, if I move it from this hand to this hand, it has not changed shape. It has not changed volume either. It has not, all of a sudden occupied twice as much space as it used to. It's not going to happen that way. So solids we can define as having a fixed shape that does not change no matter where they are, as well as a fixed volume. So, so when you change it, put it into a different container, it maintains its shape. So, nice things. Yeah, so it looks like also you have noticed that liquids and gases both do not have a defined shape. So if I were to take the liquid that's in my blue cup of the day, it's currently cylindrical, right? However, if I pour it onto the floor or into a different container, it's going to change its shape depending on what that container is. And the same will be with the gas as well. So if we move a gas from one location to another, like for example, the gas that's in my lungs right now is in the shape of my lungs. However, as soon as I breathe it out, it'll expand to fill the room that I'm in. So gases will also change their shape. How about volume for liquids versus gases? If we pour, a liquid from one glass into another glass, is it going to change its volume? If any of you have young kids, by the way, I forget exactly what age they learn this, but, if you pour something into like a taller glass, they'll think it has more in it. So you can kind of mess with them this way. So it's called conservation. So them learning that liquids have fixed volumes is pretty funny to mess with them. So of course, it doesn't impair them in any way. It's just normal developmental psychology. But it's pretty fun to watch your kids being like, even if they watch you pour from one container to another, they're going to say, no, this one has more than the other one. So it's pretty fun. So try it out. Okay, so liquids do have fixed volumes, and gases do not. Paulette, let's assume it all does leave. Like, it's just pretty interesting. Like, just watching it, if you have a glass that's wider versus a glass that's like narrow and tall, they're going to think the one that's tall is going to have more liquid in it. It's just kind of a fact. They think they learn around maybe 5 years old or so. I don't quite remember exactly what age, but if you have kids younger than that, you can trick them. So, yeah, let's not worry about like the one last drop of water that's left over. So, alrighty, cool. So in terms of shape and volume, we've got those covered. Let's talk about in terms of if we can mess with these fairly easily. Can I take this stapler here and easily, compress it? Can I take this stapler and change its volume by squishing it very easily? I'm not a trash compactor. I'm not one of those, like, car things where they make the cubes out of the cars. But not really, right? I can't compress this very easily, right? If I try, it's either going to break or, bad things are going to happen. So I can't really compress a solid. And the same thing with a liquid. If I were to try and take my liquid here and squish it down, it's either going to break the container or it's going to just squirt everywhere. It's not going to be able to actually squash down. So liquids will also not be compressible. Gases, however, are going to be compressible. Because they don't have a fixed volume, I can take a lot of gas and force it to go into a small area. You've seen gas tanks. A lot of you are interested in healthcare. You're going to have gas tanks all over the place. Those are compressed gases. So they've taken a lot of gas and they've forced them to go into these small containers. thereby reducing their volume. So we're going to see that gases are very compressible. And this will be important when we talk about gas laws later on in the semester. Alrighty, so who has some ideas about kind of molecularly how these states of matter look? Any ideas? Perhaps you've seen them before in, high school or whenever you took chemistry. Any ideas how solids, liquids, or gases look kind of on the atomic level or molecular level? I guess it would be pretty hard to type this out, huh? So, okay, I'll just do it for you. So, solids often, kind of, you can imagine some solids looking like this. Yeah. So gases are kind of the easy one, right? Gases, we have really kind of far apart atoms or molecules, and they're moving very quickly. Sorry, let me move our guest out of the way here. He's begging for pets. Liquids, on the other hand, are kind of like a somewhere in between these things. They're kind of not as nicely arranged, and they are, moving past each other. Whereas these guys, these gases, as you have noticed, are going to be moving pretty quickly, right? These guys just vibrate in place. Okay, the atoms in solids are just kind of bzzz, they're just vibrating there. They're not really moving past each other. They're not doing any, significant motion. In liquids, however, atoms can flow past each other. And in gases, they're just so far apart, moving very quickly, they don't even really see each other. So molecularly, that's how we're going to kind of distinguish these. And just if we think about it, two of these states of matter look more similar than the other one. Which two of these do you think look more similar to each other than the other one? Any ideas? Take a guess. Go ahead. Yeah. Liquid and solid are going to be the ones that look more similar, right? You can see just they're kind of closely packed atoms, right? Both of these have close atoms, right? However, the gases, the atoms are really far apart from each other. And that's going to be the reason that these liquids and solids have fixed volumes and are not compressible. On the other hand, because these gases are so far apart, we could force them to go closer together, right? We could compress them. We could change their volume. All right, but because, these atoms in liquids and solids are so close together, if we try and push them together, there's nowhere for them to go, right? So it's not going to work. However, with the gases, we can force them to go closer together, and that's why we're going to get some of the properties that we do get from gases. Okay? So, I would like you to know, to be able to identify, solids, liquids, and gases based on these properties here. Okay, so that's as far as that's going to go so far in this course. All right, so if you have any questions, go ahead and type them out. Otherwise, I'm going to go ahead and start our next little section here. which is going to be talking about properties of matter. All right, and so in terms of properties of matter, I will tell you one of them is the state of matter. So in terms of properties, I'm talking about things we can kind of observe. We can measure them, or we have some idea about them. If you were to say, is this little pen thing, is it black? Yes, it is, right? Color would be another property. Just things about matter that we can observe. Give me some. Give me some properties that you can think about. So, for example, this pen thing is solid, and it's colored black. Anything else about this you might be able to identify? Yeah, shape would be another one, for sure. So this is kind of cylindrical, or whatever. Yeah, smell, I guess, would work too. Texture, yeah, sure. Shape, texture, let's just go ahead and put with shape. So, pretty similar thing, right? If it's kind of a rougher shape, it'll have a different texture. There's going to also be some that we can't, directly see, right? Like texture, I mean, we can feel with our senses, but some things, we may need instruments. Okay, I'm going to go ahead and put opacity for that. That means, can we see through it or not? Or translucence, so this we cannot see through, right? So, good one there. There are some that we would need instruments to measure, but would still be properties, right? So we could say, does this conduct electricity? Does it conduct heat very well? Does this thing, is this thing strong? Is it going to break easily if we apply some pressure to it? Instead of temperature directly, I'm going to go ahead and put melting point, melting or boiling point. Everything does have a melting and boiling point, right? Those would be properties of the material. We could also say, flexibility. Is this thing flexible if I try and bend it, or is it going to just snap in half? Is it brittle? We have a lot of properties here that we can talk about. And another one that we have is kind of location, right? That's something about this pen. It is currently in my hand, in front of my face, in front of my webcam, right? So that's where it is. That's a property about it. There are some other properties that we can talk about. Freezing as well would be under there. So that'd be kind of the same thing as melting, just the opposite, right? So going from solid to liquid versus liquid to solid. There's other ones that we may not be able to kind of guess right away. We would have to play around with. Though, of course, learning chemistry, you will be able to kind of predict some of these things. Which would be like reactivity. Does this thing react with acids? Does it react with bases? Does it react with air? Does it react with water? Another important one is this thing flammable? Chances are probably not, because it's plastic. Plastics don't tend to be pretty flammable. They tend to just melt or decompose. They tend not to react with oxygen. And so reactivity and flammability, you probably would not be able to tell right off the bat. But part of chemistry will be talking about how we'll do that. We're going to see that all of these here, everything in these two columns, are physical properties. So these are ones we could measure fairly easily. We could either do that with our own senses, or we could use instruments to find out. Like, for example, conductivity, we can't do that with our senses, but it's very easy to, just hook up some electrodes to the end of this thing and see how well it conducts electricity. Just need some help doing that. However, reactivity, without knowing chemistry, it's pretty hard to guess if something is going to be reactive or flammable. And so those are going to be known as chemical properties. All right, and these are not so easy to measure. We kind of just have to have evidence, or we can use our knowledge of chemistry to predict them. All right, but we can't very easily measure them. Okay, so properties. All of these are properties of matter. There are definitely more. We could say how easy is it to flatten it? How easy is it to pull it into threads before it breaks? Those are also physical properties. In terms of chemical properties, though, it's typically just these two. All right, so the ability of something to burn or to undergo a chemical reaction, those are properties, chemical properties. Alrighty, so let's see here. What can I play with? So let's open my drawer here. Let's see what we've got. There goes my mic. Yikes. Not a good thing. There it goes again. Aha, let's see. Aha! A very important device here. Piece of paper. Alrighty. So it is 8.5 by 11, right? It's this nice rectangular shape. All right, shape is one of our physical properties, right? The fact that it is rectangular is a physical property. But look what I'm doing. Or you know what, let me make this a little bit more obvious. I have changed its shape. And look what I can do. Poof! It is now back to its rectangular shape. Yeah, of course there's a little fold here, but I reversed that. I was able to change its shape and then change it back again pretty easily, right? And now I will ask you, it's a piece of paper, right? Like, nothing hidden here. In this shape, it is a piece of paper. In this shape too, it's still a piece of paper, right? It has not changed its composition. It's still a piece of paper. And look, I can do other things. I can take it over here and move it over here. It's like I'm a magician. Look, I've changed its location. And look, it is still paper. And look, I can move it back to its previous position if I want to. So we're going to see that if we change some of these physical properties, we can have what is called a physical change. Physical change. Those would be altering certain physical properties. For example, oh, I know, it's awful. Like, the internet right now with the fires and everything is just a disaster. So, yeah, I know. I appreciate your patience. But thankfully, once I do upload these to YouTube, that tends to be a little bit easier because it doesn't demand as much internet as Twitch does. So, yeah, I appreciate your patience. So, also, if I were to, if I were to take an ice cube and I were to melt it, it's changed its shape, it's changed its state of matter. Is it still water, though? Yeah, it's not all of a sudden turned into vodka or something. Wouldn't that be interesting? Yeah, it's just water, right? And I could take that water, put it back in the freezer, and now it's ice again, right? So I can reverse these changes pretty easily. So typically, these are reversible. If I could spell, that would also be real nice. Reversible. And they don't change the composition of the substance. So if I melt my ice, it is water. If it is water, I can turn it back into ice. It's still chemically water. It's still H2O. I have not changed it. And again, I could relatively easily reverse that process. Okay, so we can change these things. Some of these like are inherent properties, like conductivity. You can't really change that. But some of these are pretty easy to change. All right, so by contrast, we have chemical changes. That would be undergoing a reaction that changes the composition. For example, that could be if I were to take wood and burn it, I would make carbon dioxide and water and soot and ash. I could make all of these things if I burned the wood, right? And we're going to see that very obviously I have changed the chemical composition of that wood, right? It is no longer wood once I burn it. It is now turned into carbon dioxide and water and soot and ash. We have a visitor. This one is Gumbo. Gumbo is like my hi sweetheart. Is like my laziest dog. Well, maybe not. He will periodically wake up like once an hour. He will come to my office. He will look for food. He'll just do like a circular food search. And then he will waddle out again and go back to bed. So you'll see him periodically. So he's actually Oz's son. I don't know if you guys have met Oz in this class yet. But yeah, he's just a little sweetheart. So there's our visitor for the day. All right, bye, Gumbo. Okay, back to chemistry. So if I were to take the carbon dioxide and water and soot and ash and put them in a bowl and mix them up, am I going to get wood again? Probably not, right? That would be very strange if you could, mix these four things together and produce wood out of it, right? Plants can do that, but it takes, many, many years, of course, and a ton of energy from the sun to make that happen. So typically, these are not going to be easily reversible. Okay, or they just simply will not reverse by themselves. You might have to put a ton of work into getting them to reverse. All right, it's very difficult to get these things to turn back, if at all possible. Sometimes like this wood thing, if you burn the wood and you try to put these four things back into wood, it's not going to probably be exactly the same wood as it was before, right? A plant does not have exactly the same wood as another plant, right? Like there's just slight differences between them. So our chemical changes are not going to be easily reversible, unlike our physical changes, which were easily reversible. And these do change the composition of whatever is being reacted. Another example would be, say, iron turning into rust. This is iron, by the way. Iron turning into rust is a chemical change, right? That is iron turning into iron oxide. That's a different chemical. And since it's a different chemical compound, it has different properties, right? That rust is, a different color. It's got different brittleness. It's, it's not strong anymore. It's powdery. But the iron, was gray silver, metallic. It was good conductor of heat, all this stuff, right? And so rust will not go back into iron unless we do something crazy like give it a lot of electricity or something like that. All right, we can, of course, brush the rust off, but it's very hard to actually take that rust and turn it chemically back into iron. Okay, not going to happen by itself. All right, and so this is reactivity here. Okay, so hopefully the distinction between physical and chemical changes is there for you. Do we have any questions on those? We'll do a couple little practice here. Alrighty. So I would like us to take the following things and identify them as a physical property, a physical change, a chemical property, or a chemical change. Okay, let's see if we can do these. So let's say we are going to take a book and move it off a shelf. Of those four things, physical property, physical change, chemical property, chemical change, which do we think this is going to be? Yeah, this is a physical change, right? We know that because something is happening, of course. It's a change. Something is happening. And we know that I could easily take this book and put it back on the shelf, right? And also the fact that I moved it off the bookshelf does not change the fact that it's a book, right? So those two hints let us know that this is a physical change. How about the ability maybe a little bit trickier here. But right now I'm just talking about the ability of paper to burn, or the tendency of paper to burn, if we give it the right conditions. What do we think that one's going to be? So we're not actually burning the paper, but just identifying the fact that it can be burned. What do we think that's going to be? I am going to agree with Sharia here. So that is going to be a chemical property, right? I'll do it in green just to like make it easier. Chemical property. So this tells us about the reactivity of this paper. It's telling us that it can react with oxygen to, make in fire to make carbon dioxide and water. That is a chemical property. So we're talking about its reactivity. Okay, however, if I were to say burning a piece of paper, that would be a chemical change, right? So changes always have to accompany something happening. Right? Yeah, there's definitely some potential energy in there too, Paulette. There is energy stored in those chemical bonds that we could release by burning it. Absolutely. But right now, let's just worry about these properties and changes. So properties are just kind of things that are. Changes are something is happening, something is going to change, right? Okay, and then let's see. One more for you. If I say paper is a bad conductor of electricity, which one of those four am I going to be talking about? Sure. Well, you can do that right after this particular one. So what do we think about paper being a bad conductor of electricity? So the first thing you want to ask yourself, is something happening in this one? Or is this just kind of a statement? Yeah, this is going to be a physical property, right? This is just something about the paper. It's talking about something it's capable of doing, something we could measure with an instrument. Yeah, it typically resists the flow of electricity, right? And that is a physical property. So that's telling us something about this paper that we could measure with an instrument. Okay, if we want to consider, ice melts at 0 degrees Celsius. Yeah, Paul, physical a physical property there. Ice melts at 0 degrees Celsius. So, just a statement. Or let's look at this. So do we see how these two statements are different? One of them is just kind of something that exists, and the other is a change that is happening. I'll make it a little more liquid water. These two are similar, right? But one of them is kind of just a statement of fact. The other one is a process that is happening. So we're going to say this one is a change, right? Because we're actually seeing the ice melt, right? Something is happening. However, the fact that it melts at 0 degrees Celsius is a property of the ice. Okay, it's just something that we can measure. We see a thermometer. We can say, okay, I'm going to put it in this ice, and I'm going to see that it starts to melt once it hits 0 degrees. That's something we can measure. And with both of these, ice and water are the same chemical compound, right? They're both H2O. We're not changing them into a different substance, right? And thinking about it, if I melt that ice, could I freeze it again pretty easily? Yeah, I could, right? I mean, it's pretty easy to do that. Put it in the freezer, it's done, right? These are both physical. So ice melting is not a chemical reaction, right? Nothing is happening there. It's just changing state. We're changing the physical property of it being a solid turning into a liquid. Changing state is a physical change. All right, and the fact that it melts at 0 degrees Celsius, that's just its melting point, or its freezing point, whichever way you want to look at it. And that's just an inherent property. Okay, nothing's happening. I'm just telling you that it melts at 0 degrees Celsius. I could tell you that it boils at 100 degrees Celsius. Also a physical property. Okay, nothing's happening. I'm just letting you know. I'm telling you facts about it. Okay, so facts are going to be our properties here. All right, does that make a little bit more sense? Does that kind of distinguish between the melting point versus like burning it? So remember, burning, we're turning it into different things. You burn the paper, it's no longer paper. However, you melt the ice, it is still water, right? It's still H2O. Okay, awesome. Good. Alrighty. Any other questions on identifying physical properties and, all of these four? Okay. Cool. So, we are happy happily done with our first chapter. Woohoo! We are now moving on to... We're going to now talk about math. Yay! So we're going to be on chapter 2A now, which is basically talking about how we're going to be using math in science, just in general. So we have a number of things that we're going to want to go over. Let's just take a moment to review some algebra. If this is, too much for you, it's only going to get worse, okay? So, you will, of course, have access to calculators and everything throughout the course, but you'll save a lot of time if you can do stuff quickly and, in your head. A lot of the math that we do here, at least some of it, can be done mentally. So, for example, if I were to say something 10 to the 6 times 10 to the 3rd, we're going to be doing a lot of stuff with exponentials in this course. So hopefully you can do this in your head. Does anyone remember how to multiply exponents like this? Since there is a little bit of lag with the chat, I'm just going to go ahead and remind us, right? Yeah, exactly. Yeah, you add the exponents together, right? So when you multiply them, you add them together. All right, and so again, same thing here. We're going to add them. So that one should be 10 to the 4th. Yeah, exactly. Very good, very good. All right, so hopefully this should not be anything totally new because it's just algebra. So hopefully we remember this. We'll remember that division is the opposite. You subtract them, right? So in this case, we'll get 10 to the negative 4. And maybe one more. Trickiest one. That'll be 10 to the 7th, right? 5 minus negative 2. Whoops. Right, 5 minus negative 2 is 7, right? We would... 2 negatives make a positive, right? So you should definitely be able to do this part at least. Okay, and it's going to, again, save you quite a bit of steps if you can do this part in your head, because we're going to be dealing a lot of numbers in scientific notation where they're going to have these times 10 to the components. Alrighty. So... let's see. Anything else I want to do about exponents? Yeah, one more thing. So just remember that, for example, 10 to the negative 3 is the same thing as 1 over 10 to the 3rd. Okay, they're equivalent to each other. So just remember, negative exponents just means it would be on the denominator. Okay, so that's our exponent review. If you need more review of this, I would go to Khan Academy, or just to be quite frank, if this part is giving you trouble, you may want to take a math class again before taking chemistry, just because this is really... this should be stuff that you guys know before entering the course. Okay? Cool. Not to discourage anyone, of course. So, cool. If we want to do some simple math, we can say, 5 times 10 to the 3rd divided by 2 times 10 to the 6th. This sort of thing I would also expect you to be able to do in your head. Remember that when you're dealing with things like this that have exponentials, you're going to want to deal with the exponent parts separately from the regular numbers. So we could say this is the same thing as 5 over 2 times 10 to the third over 10 to the sixth, right? Just separate the fraction out. We could totally do that. And so we know 5 over 2 is 2.5, right? And then this should be exponents again, should be fairly easy for us. Okay, of course you could do this with your calculator. You would get the same answer, but just think of how much time it's going to take to plug, the numbers in versus just being able to do it like this. And that will add up, over time as well. Okay. Of course, if, it's 5.14 divided by 2.68, no, you're not going to do that in your head. But something like 5 over 2, I would hope you'd be able to do, without any problems. Okay? So when we're multiplying or dividing exponentials, you can just separate them from the base numbers and do them separately. All right, so again, none of this should be new, just kind of a quick little review here just to make sure we're all on the same track and that I'm not just totally making up math rules out of nowhere. Okay. Cool. So, thankfully this number here is one that we're going to see a lot of the formatting a lot of. This is what is called scientific notation. So in chemistry and in science in general, we're going to deal a lot with numbers that are really big or really small. And so it's instead of writing them just normally with decimals or zeros at the end, we often will write them with the exponentials like this. Just to be clear, and so it's easier for us to see, okay, this thing is fairly small, and just have a rough idea of, the magnitude, how small it is. So in order for something to be in scientific notation, we want to have some number decimal these are all kind of optional numbers, however many we need, times 10 to some other number. So you always just have one number before the decimal. Let me make that a little neater. So for example, this 2.5 times 10 to the negative third, that's the same thing as 25 times 10 to the negative 4, right? Same number. However, the one in green is not in scientific notation because we have more than one number before the decimal point, right? The decimal point would be here if we wanted to put it there. And so having two numbers before the decimal is not scientific notation. So whenever we're talking about scientific notation, we have to have just one number. So for example, this 2.5 has one number before the decimal, and it doesn't matter how many numbers are after the decimal. All right, and then we have times 10 to the negative 3. So we'll be practicing now putting numbers into scientific notation and also converting them from scientific notation to just like regular numbers. So hopefully you also all know that if we take that 2.5 times 10 to the negative 3, that's the same thing as saying, we have to move the decimal over 1, 2, 3 spots. And so that number is also written like this. These are the same number. The one in black is in scientific notation. The one on the right is just a regular number. Okay, again, mathematically, these are equivalent to each other. Remember that a negative exponent, that tells us that this number should be a small number, right? And if our exponent were positive, that lets us know we're working with a really big number. So for example, if we had 6.21 times 10 to the 5th, positive exponent tells us we are dealing with a big number, right? And so we're going to see that in order to convert this number into regular notation, we would have to move the decimal over 5 times. 2, 3, 4, 5 times. And so we should end up, we moved it 1, 2, 3 more zeros. That's going to be the equivalent number in standard notation. Okay, we just have to put the zeros there to make this 621,000. It's the same thing as 6.21 times 10 to the 5. Exactly the same number, just written in different ways. Okay, so if we have a negative exponent, we are going to move our decimal point to the left. So let's do that in purple. So you saw on this example, we moved our decimal point to the left, and we have to fill in kind of those blank spots with zeros. If it's a positive exponent, that indicates a large number. And to convert that into regular notation, we move the decimal to the right. So again, hopefully none of this is new information. Maybe it's, in the back of your head somewhere, and maybe just takes a little practice to get back into, having these kind of easy in your mind, and that'll be okay. But this should not be totally what the hell? How is this possible? So, again, just letting you know. Okay, so far so good. Okay, cool. So going backwards, we can do the opposite. Let me actually move this down a little bit. It goes backwards. It's going to be the opposite of last time. So whatever that was, 3612 I think I put as the number. If we were to convert that to scientific notation, okay, sorry, Paulette. Yep, I totally get it. Thankfully, all these are totally available for us. So we know the decimal is going to be there in this number, right? So if we want to move this decimal such that we have only one number to the left of the decimal point, we'll move it like this. 1, 2, 3 spots, in this case, as far as we need to move to get it so there's only one number on the left of the decimal point. So that tells us this is 3.612. And then we notice we had to move the decimal over 3 times, right? And is that going to be positive or negative 3? we look at this number, it was 3,612. That's a big number, right? Relatively speaking. Big number, positive exponent. Alrighty? And so remember, when we were taking a big number and converting it to a scientific notation to a regular number, we move the decimal to the right. If we're doing the opposite, we go backwards. We move the decimal to the left. All right? You always want to move your decimal so that it has one number between to the left of the decimal point. Okay? So, if we have a real small number now, I don't know, 5,4, we can do the same thing. So 0 is not going to count as a number. We want a number between 1 and 9 that is going to be in between, or that's going to be one of those numbers to the left of the decimal point. All right, so we're going to move this over, in this case 3 times, and that will give us 5.4 times 10. And if you look, we moved it to the right 3 times, and we know small number, this will be -3. Okay? If this is troublesome, I would go ahead and take a look at Khan Academy's scientific notation page. That'll give you another bit, more practice with this. But this should not be too new for any of you. Alrighty, so it looks like we are out of time. So we will continue. We'll start off with a few practice of these tomorrow, and then not tomorrow, next week. Enjoy your weekend. Have fun. So I will see you guys on Monday. No homework yet. I will probably give you your first homework assignment next week, probably Monday or so, maybe Tuesday, depending on how much we cover. So, alrighty. Have fun, stay safe, don't burn, and enjoy your weekend, everyone. Take care.